Good morning, everyone. Welcome to this joint workshop between LIGNICOAT, THERMOFIRE, and Viable. It's a pleasure to welcome you today. We will talk indeed about bio-resins and flame retardant for coatings and additives. The goal of this meeting is to share knowledge among the results and the research that has been generated by these three projects, and so to raise a bit of your knowledge regarding bio-based coatings, bio-based compoatings, and also look at the development and the market adoption, and also we will have a section on application. Regarding general rules, before you ask, at the end of the meeting, maybe the next day, all participants will receive the slide, so don't worry about that. And with the slide you receive, we will also publish the recording of this meeting, which will be available publicly, so it will be uploaded on YouTube. And And at the end of the workshop, there will be also a roundtable discussion. So that's why you want also to stay until the end and also stay after each presentation, because we will have a question and answer session. So for today, I think you cannot see my screen. So for today, we will have different speakers. We have project coordinators from Tecnalia, Aitor. Then we have project coordinator for THERMOFIRE, Elvira, and technical project coordinator from Life Viable, Mark. We will also have some experts regarding epoxy and also application of alkyd coatings and for flame retardant. So we have Christine, Saulo, and Claudio. And for today's agenda, we will start with the introduction of each project. So it will be very brief, just to make you familiarize what all these projects are about. So what is LIGNICOAT, what is THERMOFIRE, so LIGNICOAT, you will see it, and also Viable as well. Then we will start the practical part, and we will have a section on bio-resins and coatings and composites, where Christine and Mark will have a presentation on this, and around 20 minutes, and then there will be a little part for question. After that, we will have a session on flame retardant additives for composites and coatings, and then we will have a break. Then we will go into the application part, seeing some example for alkyd, for flame retardant with Saulo and Claudio. And then there will be an interactive part where we will be using some tool like Slido for seeing what you think about. We will have mainly 4 questions. So about the main benefits of this bio-based materials that you've seen during today, what are the main barriers, what policy should do, and what could be the possible future scenarios. And then we will try to wrap up, and we will conclude. So with this, I will kindly give the floor to Aitor for the first presentation on LIGNICOAT.
Thank you, Michele. Okay, so thank you very much for attending this workshop between these 3 projects that are focused on sustainability and bioproducts and also fire. In case of LIGNICOAT, the focus of LIGNICOAT is the coatings, improve not only the bio-base, but also the sustainable content of these coatings. As you know, one of the main challenges in the coating industry is the reduction of volatile organic compounds that have regulations issues and also have some hazard issues. So this is the general scheme of the project. As the title can show, we focus on lignin as a starting material. There are other bio-based material like oils, others that are used in coatings industry, but in LIGNICOAT we have focused in lignin, different types of lignin, mainly craft, organosulf, and hydrolysis lignin. We prepare, the objective is to prepare resins with this lignin, not just use lignin as a part of the coating, just prepare the resins, not like additives, like a resin. So we need some intermediates. We need to modify this lignin. So we have different approaches. The first one is produce polyols from these lignins. The second one is polyacids, and the third one is epoxidized lignin. With the aim of prepare alkyd resins, epoxy resins, and polyurethane resins. The main application of these resins will be wood and metal protection. Taking into account the performance of lignin and the characteristics of the lignin, we focus on fire protection, anti-corrosion, and antimicrobial and antiviral and bulk degradation performance. In parallel to this, in order to increase the bio content of the coatings, we have devoted work package for the developing of bioadditives. One of them are enzymes for bulk degradation and other active compounds for fire performance and also for antimicrobial and antiviral performance. The main applications of these coatings could be furniture, automotive, flooring, machinery, and paints industry. Here you have some examples. The project is close to finish in November, so we have quite a new development. So the first one is the polyurethane-based coating based on the developed lignin polyols. You have here some pictures. Other development is the alkyd resin that is based on lignin polyacids, modified lignin polyacids for protection of metal. And also we have formulated epoxy lacquer for coil coating on aluminum. The main goal is the reduction of carbon emissions by 20 to 50%, and also increase, as commented before, the bio content. We are between 10 and 60 depending on the technology. So the impact is the creation of a new cross sector, because the lignin currently is not used in the production of resins for coatings. A new bio-based value chain based on this raw material and the final applications. The new developed chemicals like lignin polyols, epoxides, and polyacids could be a product, a new bio product for other applications, and the same for the bio-resins, polyurethane dispersions, alkyd, and epoxy. And as commented, we have an objective of obtaining more than 25% of bio-based content. And the idea is to create new jobs based on these new technologies. This is the consortium. We are 14 partners from 8 countries, 9 industrial partners, 4 RTOs, and 1 non-profit organization. Here you have the map, and you have we are more or less in Europe. And this is all for my part. Thank you very much for your attention.
Thank you, Edor. I think we can proceed with Elvira. You're welcome to say us more about THERMOFIRE, about the bio-based flame retardant and the bio-based fibers that you develop.
Thanks for the introduction, Michele. Yes, I'm going to share my screen also to present the THERMOFIRE project. Thanks for the invitation to taking part in the workshop. And I'm presenting THERMOFIRE project, which is a CBE founded project in the call of 2022. So the title of the project is Bio-based Fire-retardant thermoplastic composites reinforced with natural fibers. And we are encouraged to do a 100% composite with bio-based materials. So we are working with polyamide 11, a bio-based polyamide 11, bio-based fibers that I'm going to present in the second part of the project, and bio-based flame retardant additives. And then, of course, we have to integrate to finally achieve a performance, an adequate performance of the composites. So, as I told you before, we are designing, developing, and validating novel and lightweight bio-based recyclable thermoplastic composites with enhanced mechanical properties, but also fire resistance by the incorporation of natural fibers and bio-based allergen-free flame retardants. We are a consortium of 12 partners coordinated by us, and we are using 100% polyamide 11, which is developing Arkema, and we are focused to prepare 3 prototypes at TRL5 in the automotive sector, aerospace sector, and textile for building applications. The final goal of the project is the removal of the European dependence on the fossil-based polymers as much as possible and increasing the sustainability of the composites, addressing these new methods for the preparation of biopolymer and bio-based composites. So we are trying to move from the lab scale production in some cases to the industrial scale. You can see here some of the prototypes that we are aiming. It's the aircraft interiors in the seats and also the battery case for the electrical vehicles in the automotive sector. We have a contribution near to 5 million euros from the CBE. We started in 2023 and we are ending in 2027. We are not so mature as in the case of LIGNICOAT, which is reaching the end. In our case, we are about 1.5 years, more or less now. And as I told, this is the products that we are developing. In our case, we are not so well balanced. We are more in the south of Europe. We are composed by 2 RTOs, 6 medium small companies, and 4 large companies. We are more in the South Park with Italy, France, Greece, and also Spain partners. And as final goal, a part of the 3 types of demonstrators that I commented for the 3 industrial areas, the aerospace, automotive, and textile applications, our goal is a reduction about 20% in the weight and 30% in cost, while it's very important we are able to keep the required levels of safety, not only because of the mechanical performance, but also of the flame performance in the composite that we are developing. So we are really encouraged not only to have a good additive, a good bio-based additives and composite, but also a good performance and looking for the market acceptance of our products. This is more or less our introduction, and then we will disclose more details on the materials.
Thank you very much, Elvira. I think so far we already saw that 2 different projects, but with the same aim of developing something that is both technically feasible, but also economically viable. And now we can also proceed with the viable presentation that they are aiming to replacing BPA, bisphenol A from the formulation of epoxy resins. So without further ado, please, Mark, tell us more.
Can you see my screen?
Yes.
Well, first of all, thank you so much for this invitation to this workshop. It's a pleasure for me to be here since I've been collaborating in both projects, in LIGNICOAT and Life Viable, but this time I will present a little bit of what Life Viable stands for. Life Viable is a project that is receiving funding from the European Union Life Program, and the acronym stands for valorization of lignin biomass into competitive components, gradually replacing BPA in the formulation of epoxy resins. And it's because on Life Viable, we center mainly in epoxy resins. As you know, epoxy resins are materials that are very rigid and very useful for hard conditions because they have very good resistance to thermal conditions as well as chemical. But one of the problems is that they contain one of the main components that they contain is a epoxide that comes from a bisphenol that have some safety concerns. The growth market of the epoxy resin in the next 10 years is going to grow up to 7.3%. That means that the use of this bisphenol is going to increase, and this represents a problem not only for the landfills, but also because part of this bisphenol A that is not reactive during the glycylation process, it can migrate during the use of the material and can contaminate the ecosystem and also the humans. Has been detected in different studies in Canada, in Australia, in USA. Humans are having presence of BPA of these bisphenols in their urine and blood, which is a high concern because it affects is an important endocrine disruptor, mimicking the activity of the estrogen and affecting the reproduction of the not only human part, also small ecosystems. For that reason, the challenge of Life Viable is, can we replace this aromatic bisphenol fossil base for something that is bio-based? And here is when enters the lignin. So for Life Viable approach, we selected 4 lignins, which we believe that are currently available in Europe. And what we are doing with these lignins is treating these lignins because they cannot be used as such, since lignin is a very complex aromatic random biopolymer. We are treating them, we are solubilizing them, we are depolymerizing them in order to make a more defined building block, and we will use this building block partially replacing from 25 to 50% BPA in the formulation of epoxy resins. These epoxy resins are going to be used to synthesize prepregs that are going to be used in the different parts of automobiles. What is the important part of Life Viable that differentiates Life Viable from, for example, LIGNICOAT, is that in this project, we don't focus as much in research, we focus in scale up the process. So we started at laboratory scale, testing all of these kind of lignins, selecting which is the best one, doing life cycle analysis of which one could be viable, reliable, and reproducible for a big process. And then we are passing to a continuous process that we tested in the laboratory, and then finally to 2 pilot plants that we have here at Pito, able to depolymerize lignin. So Life Viable partners, they are around all the value chain of the epoxy resin market and composites. We have the biomass producers, the lignin treating producers, and that they polymerize, the ones that are fabricating the epoxy resin, the ones that are fabricating the prepregs, the one that are adapting these prepregs to the form of the material that we are going to use in the automobile, and the ones that are testing already in the car. Also, we're having some partners that are taking advantage of all the studies and all the calculations to estimate the life cycle analysis. And also we have partners that are more related with communications. Vito is leading this consortium, but also there is Westlake Epoxy that you will have a speech later, Ciensco, Apesa, HP Composites, CMB, Stellantis, and Polymeris. If you want to follow us, guys, here I let you the website, some emails, LinkedIn, and Twitter, and I invite you to subscribe to our newsletter. Thank you for your attention.
Thank you very much, Mark. It was good to know also about Viable and how it differentiates from LIGNICOAT, but there are still some shared purpose here. Now we will start. I think we're a bit ahead of schedule, but I think it's okay. We will start with the session on bio-resins for coatings and composites. Here we will dig more into epoxy resins. So we will have a session from Christine from Westlake Epoxy, and then we will see more on LIGNICOAT, and then we will see more about Life Viable again with Mark. It's a pleasure to welcome Christine from Westlake Epoxy.
Thank you very much for the introduction and also for the invitation to be able to join this workshop today. Yeah, my name is Christine Baron. I'm a sustainability innovation scientist at Westlake Epoxy. I started 2 years ago as a R&D trainee for Westlake Epoxy, and I had the opportunity to work in several departments all around the R&D and leading projects always related to sustainability. So now I'm more than happy to share that I started my new role as sustainability innovation scientist. Today I would like to show you the LIGNICOAT project and lignin-based epoxy resins where we precipitated. But I would like to start to introduce you first to Westlake Epoxy. So who we are. Westlake Epoxy is a special chemical producer. We produce epoxy resins and epoxy resin formulations, which enables our customers' individual products with a characteristic performance of strength, heat, corrosion, chemical resistance, and also in addition to superior adhesion. We as Westlake and also as Westlake Epoxy do have very clear goals on minimizing our climate change impact. First of all, this includes to reduce the scope 1 and 2 emissions and to reduce the greenhouse gas emissions. Above all, we also want to reduce the scope 3 emissions, and that mainly goes to more renewable content and bio content, which is also the main topic of my talk today. Another point is to increase the product circularity by using internal and external waste streams, which also belongs to the scope 3. And further than that, we are always looking for new innovative solutions to reduce the carbon footprint and enable circularity in all of our products and formulations. And we are more than happy and proud to say that we are once again been awarded by the gold medal of EcoVadis for the sustainability rating 2024. But talking about epoxies, how do we get from our known system to a novel biosource? We produce bisphenols, which you can see here on the right. Undergoing a glycidation reaction, these bisphenols forming epoxy resins with an epoxy functionalization. The most important property of our products, our resins, is the aromaticity, which leads to the unique properties of strength, heat, corrosion, and chemical resistance. And this aromaticity is also given by bioaromatics, which could like this. And so these are becoming a very promising candidate as a building block for new sustainable resins. And this brings us already to the first generation of lignin epoxy resins. What we did as Westlake Epoxy, first we tried to use technically available resins, like craft resins, and did our first process development with these resins. And for sure, we had a little bit issues, and this really needs some time to be able to work with these new biomaterials. But we found a solution, and we were able to use these bioaromatic epoxy resins and produced on lab scale first samples. These one we could send over to our colleagues of the product development and application, where they can test coatings or composites from the formulation with the final goal to have the first bioaromatic systems. By using all our in-house options that are available to us, we were able to develop an optimized screening method. The beginning of our variable chain starts with the process chemistry itself, where the new substrates can be tested with new processes. Starting with the scale down, with the very smallest scale, by using 5 ml reactors, up to 50, 500, and in the end 3 liter reactors, before they are able to be tested in our pilot plant of 300 liters going to a production size. During the process development, our analytical team can perform the inline analysis and perform in-depth analysis and characterization by using NMR, GPC, and other analytical methods. As soon as the process now is running safely and the analysis has been fully clarified, the material can be forwarded to our colleagues of the application development. Initial tests can directly validate the material and provide some feedback to if there are needs to change the process or to find with the major goal always to find the best possible solution for the customer. And of course, we needed several feedbacks loops going back to the analytic department, even to the process chemistry, to end up in the final formulation. To evaluate the structure properties between the bioaromatic many fragmentation methods and also for the products, we try to use the largest possible network to generate the maximum success and to test all possible fragmentation methods, starting with pyrolysis over fragmentation, depolymerization, solvolysis, and extraction, always with the goal to have a glycidated product in the end. And depending on the final application of our customers, we need to have a broad portfolio of different epoxy resins to suit even the different fields of interest. And here's the key point, really. Collaboration is key to get the maximum effort and the maximum environmental benefits from these bioaromatics. And this brings me already to the Bio-resin network, where we are more than happy to precipitate. So we as Westlake Epoxy did our first in-house tests and screened material, and then coming to Bio-resin to expand our research network and also working with various projects to form a value-adding chain and to be able to work with other industry partners that allows us a faster lead generation for specific applications. By joining the Bio-resin network, and Mark already briefly explained something about the fragmentation of the lignin, we receive these lignins and then be able to use it for the LIGNICOAT project and also for Life Viable. Therefore, I would like to start with the results of the LIGNICOAT collaboration. And Aitor already described a little bit the project goal of LIGNICOAT. So also from our side, the project goal is to develop and also to produce a coatings formulation for coil coating and also for ambient cure systems that are based on lignin. And then using these bioaromatic systems that we received from Vitro, which you can see here on the left-hand side, very brownish solid material, started our in-house process development on the 250 ml reactors in our labs in Pernis, Rotterdam. And when we are able to finalize these process settings and also having the whole analysis together, we send the material over to our colleagues in Duisburg of the product development and application. And you can even see the plant in the background. So they did the first tests and formulated different types of coatings. So to come to the results of the coil coating applications, first of all, epoxy lignins do have different polarities, belonging to the process itself, also belonging to the glycidation reaction in comparison to standard epoxy resins. So we first need to start with the solvent screening to conduct the best suitable solvent. Out of that study, we could have the first results of epoxy lignin resins that unfortunately show a little more brittle than the reference, cured with phenol epoxy resins. But by the use of an MEK double rub test, we could see a complete curing that can be achieved. And based on these new lignin resin formulations, we have been able to develop coil coating formulation and also ambient cure coating. A lab curing process can be implemented and also tested in comparison to commercial reference. And these formulations that we produced are now sent to IEP polymers for the further validation and the final development of these coil coating formulations. Our next goal was also to develop an ambient cure application. And based on the successful development of our glycidation process and also of our ongoing development with the different lignin upstream processes, we could start to formulate and to improve the performance. As I already mentioned, we did a solvent screening and same for the ambient cure system. First of all, these solvents needs to be adjusted for new resins. And for the ambient cure system, we could find that propylene glycol monomethyl ether can be used in that case. And the test with a modified polyamide curing agent could already show increased hardness, tested by Koenig hardness, and also the mechanical performance by Impact and Ericsson in comparison to Westlake epoxy reference shows increased development. So in the end, I would like to thank, as I already mentioned, collaboration is the key and also teamwork. And this was a very big project from our project development team in the Netherlands, as well as the product application and development team in Germany. So it was a big effort. It was always fun to work in this loop and be able to going back to the start where the process starts to the analysis and even to the end application. That brings us all a lot of fun when we reached success in the end. I also want to thank the LIGNICOAT project and also Life Viable, because without all these cooperation partners, we were not able to gain so much experience in such a less time, and also be able to share our experience during the development. So thank you very much. If you want to learn more about the LIGNICOAT or even Life Viable, you can find these websites here. Also my email address if there are still any questions opened. And I'm happy to hear questions from you. Thank you.
Okay, they are asking, one of the participants is asking is there a study comparing UV resistance and alkali resistance in long-term tests? I'm not sure if this is...
Yeah, good question. Tests are planned but not conducted yet. But of course, that's a very important point for us because, of course, due to the aromaticity, we always need to have a stable formulation that is UV resistant.
Maybe I can also ask a question. In one of the first slides, you presented how Westlake, let's say, develop the process, and you have like an iterative loop between three processes, like process chemistry, analytical chemistry, and application development. Where do you see usually where you have the most, between which two of these two processes you have the most iteration, or where are the main challenges here?
Hard to say. I would even say in all of these departments, because starting with the process, it's not easy, especially by handling biosubstances. They have a different solubility, different behavior, and you really need to change your process and be open to use new processes compared to our standard epoxy resins. So that's a lot of effort, but also inside of the application development, because you now have a brownish material that's maybe not that soluble like any other resins. And then having a clear coat that can be cured by ambient temperature, that's also challenging. So I think it's hand in hand, very on both sides. And in the middle, the analytical part, also hard because, again, it's a biosubstrate, a huge molecule, a macromolecule, and it's not easy to analyze every detail of such a big molecule or be completely sure how the molecule looks like in the end. So I think the effort was on every department.
Okay.
Same share.
Okay, I see. Thanks. So I would like to thank you very much, Christine. Very insightful presentation on Westlake and epoxy. Mark, if you want to go ahead with your part, so we can learn more about Viable, you are very welcome to share. Okay.
So at the start, I introduced Life Viable as a project that intends to replace partially the bisphenol A content in epoxy resins by something more sustainable, more bio-based, like lignin. But in this presentation, since I was expecting my colleagues Christine, Elvira, Saulo, Aitor, and Claudio to go more through the properties of the material, I would like to relate my presentation more to the source, to the lignin, how we treat the lignin, how we depolymerize the lignin, and how the different structure of the lignin is related with the final bioresin, and what are the similar parts with bisphenol A and what are the parts that we cannot compare at this moment. So the title of my speech is Lignin as Sustainable Alternative to Gradually Replace Traditional Bisphenols in Thermoset Industry. And hopefully at the end of this presentation, I will convince you that if lignin is not yet the panacea to substitute all the fossil-based bisphenols, at least is a reliable and viable solution at this moment. So let me go through my presentation. So a little bit of introduction. We are not talking about all the kind of polymers here. We are talking only about the thermosets polymers. They are these polymers that one time they are cured, they cannot be modified. Are these polymers that they have high resistance to the thermal conditions and the chemical conditions. They are very tough, they are very rigid. And there are different types of these polymers: epoxy resins, phenolic resins, polyurethane resins, benzoxazine resins, melamine formaldehyde. But we are going to focus, because since in the Life Viable project we are focusing the composites made of epoxy resins, we are going to focus in the epoxy resins. And you will allow me to establish this general reaction that I know that is not for all the epoxy resins that exist in the market, but more or less the general ones are made out of an epoxide component, where R usually is a fossil-based bisphenol and a hardener that usually is a diamine. By thermal conditions, we cure these two components, fabricating a cross-link high density network that allow us to use this kind of material for high-tech applications like automobile, technology, construction, satellites, flooring, renewable energies, etc. With this presentation, I don't want to criticize so much the role of bisphenol A have taken all of these years. Epoxy resins are more than a decade old. They were invented during at the end of the second global war, and they were used as utilities for dental purposes at the start. But during this almost century, bisphenol A have developed a role very, very important on these resins, and is that their structure is so well defined and it gives so much properties to the end structure of the material and is so useful that for that reason have not been substituted for anything else. But there is a problem. This bisphenol A, unfortunately, can mimic some of our parts of our human body, like the estrogen, and can activate some of the receptors, not allowing the receptors to get the natural activators, no? And also, what is happening with this bisphenol A is that sometimes during the process of the glycylation to synthesize diglycylated bisphenol A, there is unreacted bisphenol A that then cannot be included in the formulation because the phenol doesn't react with the diamine. So it gets unreacted in the material that sometimes can migrate and can get leached to the human or to the ecosystem. We know that in Europe, there is already quite regulations in the use of bisphenol A for polycarbonates that are getting in applications like toys, like baby bottles, like packaging of food, or like thermal paper. But now we are listening rumors also that in the next years, there is a increasing concern for all of these coatings made of epoxy resins based of bisphenol A that are in direct contact with water. That means piping of water, but also flooring. Because when in the floor, we need to clean this floor, to wash this floor, we are using basic conditions that we can remove part of this bisphenol A that is migrating and then dropping this bisphenol A in the ecosystem. So what we have is a maximum component that is this one, diglycylated bisphenol A, that is made of deglycylation between bisphenol A, as I put you here in the reaction, and epichlorohydrin. Epichlorohydrin, now there is already companies in Europe that are investing in making full bio-based epichlorohydrin from glycerol and water salty water. So we are going to try to substitute or replace partially in life viable the other component, the component that is the diol or the polyol that is between these two epoxide modifications. One of the most abundant source of natural aromatic in the nature is lignin. Lignin, together with cellulose and hemicellulose, it forms part of the total biomass, and all the vegetables contain lignin. But in the current process, only for the industry of the paper is fabricated the lignin or is obtained as a byproduct of the industry of the paper and bioethanol industry. And out of these, 95% of this product, lignin product, is incinerated because there is nothing more important to valorize this lignin. So it costs less to incinerate and use this energy to produce, to run again the industry of the paper or the biorefinery of the bioethanol. Also, lignin is a renewable and biodegradable compound, since it's coming from vegetables, is renewable and biodegradable because there are literally some fungi and some bacteria that can degrade the lignin. And as I told you, is a potential substitute of bisphenol because share part of the structure. It's not as defined and as traditional fossil-based bisphenol, but shares partially the chemical structure. So in different vegetables, we have different content of lignin, as I put you here in this table on the right. And we are going to select for life viable 4 out of all of these different botanical origin and vegetables. But lignin cannot be used as such because lignin is a really complex biopolymer. So we need to treat this biopolymer. We need to solubilize this polymer and discard the insoluble part. And out of the soluble part, we need to depolymerize in order to make building blocks that are more defined and more reactive. So here is where it comes life viable. As I explained to you before, life viable is a group of partners that we are covering all the value chain of the composites made out of epoxy resin, and we defined our project in 4 stages that are increasing in the upscaling of the process. At the first stage, only for biomass producers and lignin producers that we are testing the botanical origin of the lignin. What is the composition, what is the structure, what is the solubility, is this lignin ready and correct structure to make epoxy resins. We will test in this stage. In the second stage, one time we pre-select some of the lignins that we are going to optimize the process. We are going to increase the yields. We are going to go for solvent recycling. We are going to go for more reproducibility. We are going to go for, we're going to improve the process. Then in the stage 3, we are going to upscale from grams lab scale to kilograms. And not only that, also we are going to try to go from batch reactors to continuous reactors. And in the last stage, we are going to go for pilot plant production, and we are going to demonstrate that the use of lignin as a bioresource in order to make epoxy resins for the production of biocomposites is something that is reliable and viable. So let's go for the first stage. Out of the a lot of different botanical origins that there are in nature, we select these 4, and is for more availability in worldwide. This is sugarcane bagasse, then corn stubber, hardwood, and wheat straw. Out of these, 3 of them, they are grasses. The grasses are known in literature that they are containing more phenol group, that this will help us to modify and glycerylate in order to make bioepoxide resins. So as I explained you, the lignin is a very complex aromatic biopolymer that contains different reactivity and different solubility. The main reactive groups in lignin are the aliphatic OH, the aromatic OH, and the carboxylic acid. That usually the carboxylic acid, they are in much less ratio than the other ones. So what we need to do in the raw lignin that we are receiving from the biomass producers is improve their properties. And 2 of the properties that we want to improve is solubility and reactivity. The lignin that we receive from our suppliers have a high molecular weight and a high polydispersity. That means that the solubility is very bad, but also the chains are so much different to each other that we need to get a more defined product. Also the reactivity, since the molecule or the biopolymer is so dispersed and is so big, the quantity of reactive points is very less. It's these reactive points that the ones that we are going to try to modify later and glycerylate. So what we do is at the first stage, we start lab scale with a batch reactors. What we are doing is a reductive catalytic depolymerization, and we are targeting mainly these ether bonds that they are in the lignin, these beta of 4 ether bonds. When we produce the break or the hydrogenolysis of these ether bonds, we create new phenols and more defined and more small molecules. So usually our target is passed from raw materials, lignin raw materials that have molecular weight between above 5,000 kilograms per mole or 5 Daltons to less than 1 Dalton. And dispersity that is going from 3 to 5 to less than 2. Also, it's very important for us the increase of the OH content that needs to be more than 6 millimole per gram. What we are doing later is this phenol that we created by the break of the beta-O4 ethers. We are modifying with epichlorohydrin, creating the glycerylate lignin. It's very important for us also to measure the epoxide content in order to make it comparable with the commercial the glyceryl ether bisphenol A. So at this moment and at this stage of the process, we target which one of these lignins was not the best, if not what was more available at Europe. And we have seen that sugarcane bagasse, unfortunately, is more abundant in Brazil, in Indonesia, in China. So the cost of bringing this kind of lignin here to Europe was destroying our life cycle analysis. The calculations, the estimations were getting so much expensive. So we decided to discard sugarcane bagasse for the second stage of the process and continue only with corn stobber, hargood, and wheat straw. So for the second part of the process, for the stage of the project, process optimization, what we tried is that with the rest of the lignins, go bigger. Not only go bigger, go more continuous. We pass from batch reactor in lab scale to continuous reactor, from producing 20, 30 grams per batch to a stable production during different hours of 10 grams per hour. This allowed us to treat this lignin, solubilize this lignin, and when this lignin was solubilized, put it in the continuous reactor, but here we face a different challenge that in the batch reactor we didn't face. That is the feed flow rate, so it depends of the concentration of the lignin in solvent that we are introducing in the continuous reactor, the gas stream rate, because as I explained you, this is a reaction of hydrogenolysis, so you need constant rate of hydrogen. And if you get a shortcut of this gas, what is happening is that you don't create this phenol that you want to create, the reactive point. You are creating other modifications that don't serve for the further modification that is the glycerylation. So it's very important that the gas rate of hydrogen will be constant during the process. Here also, in comparison with the batch reactor, we can play also with the temperature. We don't need to maintain the same temperature always. In different part of the continuous reactor, we can apply gradients of temperature that this allow us to target different ether bonds that there are inside the lignin molecule. And also, a big difference between the batch reactor and the continuous reactor is that we can monitor what is happening inside the reactor at different times. Batch reactor, unfortunately, when it finishes the reaction, we have our results. We do phosphor NMR, we do GPC, we see the molecular weight, and we see the OH distribution, and we are happy. But in the continuous reactors, we can see every hour or every time, every choose time that we want, what is happening inside the reactor and how the lignin is getting fractionated with the different conditions that we are applying. And this is a very important information for us. So what we did later, when we get our depolymerized lignin that have had the parameters that I showed you before, is glycerylate this lignin, and here in the process optimization, we took into account or we considered different things. This depolymerized lignin that we obtain is soluble. It reacts well with epichlorohydrin. What is the yield of the epoxidation? How is the workup? And different other parameters. And when we have had this glycidylated lignin, we send it to our partners, the ones that are producing the materials, and they did our lignin-based materials. Case of the different properties that they were measuring, they were doing like more square samples or like more coatings. In this case, we needed to pass to stage 3, that it was upscaling process, and we have seen that corn stubber, unfortunately, even if it's a lot available in Europe, is very difficult to dry. So corn stubber is a vegetable that when we have the biomass, is very difficult to dry, and the biorefineries are not ready to invest money in this kind of obtention of lignin. And on the other hand, we have seen that wheat straw have had very a lot of solubility problems. So it difficult a lot the process of depolymerization and the process of glycidylation. So we decided to discard these two botanical origins and move forward only with hardwood that is well established biorefineries in Europe. So in the stage 3, we went even bigger. We passed from mini continuous reactor to the pilot plant, the polymerization reactor. Our pilot plant that we have here at Vito is called LIGNICOAT. And we produce kilograms quantity for our partner, Westlake. And here we faced a different challenge that we have not faced before, because it's as we are like a research institute, so we are not used to handle this in industrial quantities, and we have had some problems or issues or challenges that we already solved in order to handle the big amounts. We needed to think, when we go so big in the solvent recyclability of the process, of the product isolation, it gets more tricky when it gets bigger. The production times is also something important. We are not talking here about the technicians in the laboratory. We're talking about operators in the pilot plant. And also what is really, really important is the process monitoring, what is happening inside the pilot plant, because it's not the same to lose some grams per hour that lose kilograms per hour. It's a lot of money that we are wasting there if the process goes wrong. So after we produce our kilograms of lignin, we deliver to Westlake, our partner in the consortium, and they are studying different ways in order to glycidylate this lignin in large scale. They are doing the studies in Rotterdam and for later pass to Duisburg to their pilot plant. What is very interesting of this stage is also that we are trying to compare the ecotoxicity between our depolymerized lignin and bisphenol A. And what the feedback that we are receiving is that the human exposure, and we are talking about like eye irritation or cutaneous irritation, is much less from our lignin than from the bisphenol A. Then we also did tests about the reproductive alteration of the zebrafish, that is this fish that you have here. We put these fishes in different environment with bisphenol A and environment with a little bit of our lignin in the same conditions, and we have seen that we didn't alter as much the reproductive cycle of this zebrafish when he is in environment with lignin that when he is in bisphenol A, which is really good news also. And finally, the endocrine disruptor. So we measure the activity of these receptors, and we have seen that lignin activity is 100 times, 2 orders of magnitude lesser than bisphenol A, what is really good news also. All of the results will be published in a few months in literature. We are planning to publish in the next month. So next step, and the current step where we are now, is that in the stage 3 process of scaling, as I explained to you, our colleagues from Westlake, they are trying to get glycolated or lignin-based epoxy resin fluid in large scale in their laboratories in Rotterdam and Duisburg, and they are passing their formulations to our colleagues of Ciensco, that they are trying to make a good formulation to prepare the prepregs, that at the same time they are passing some of the materials that they are already testing to our colleagues of HP Composites, that they are trying to make the first prototype. And in the other, on the other hand, also we are in the stage 4. So that means that we need to fabricate 150 kilograms of the polymerized lignin in the last stage of pilot plant production at Vito, and we incorporated a second pilot plant that is called Pillar 2 that allow us to solubilize these big quantities of lignin, discard the insoluble part, pump the soluble part to lignovalue to depolymerize, and then to get the depolymerized lignin. This is going on now. We started is working smoothly in lignovalue, but we have some challenges now in order to pass the solubilized lignin from Pillar 2 to lignovalue that we are trying to resolve at this moment. So future outlook, Life Viable is not as advanced as LIGNICOAT, so we are still, I will say that it remains 1.5 years, 2 years to finish Life Viable. And what is important of this project is that we need to demonstrate the last stage of the project, that is the pilot plant stage, that we are able to do in a reliable and reproducible and viable way the production of lignin-based precursors, to push the gradually replacement of these bisphenols and make it as a real solution for the industry to substitute partially this lignin for bisphenol A. But this push not only need to come from this private fund or European funding, or in this case projects. Also, we think that in the next years there will be a kind of more regulations in the European Union in these directions that we will push us to go to these renewable solutions. And the conclusion, I hope that I convince you a little bit, is that maybe lignin at the current stage is not the panacea to substitute for all the applications the total quantity of bisphenol A in the composition of epoxy resins to make composites, but at least for some applications, partially substitution is a reliable and viable way to produce bio-based composites. As I told you before, this is our team. Thank you for your attention. You are invited to join us in this way, and please register to our newsletter. And if you have any doubt or any question, it will be my pleasure to respond.
Hi, Mark. Yeah, it was a really illustrative and also very stimulating presentation. I really enjoyed so much. And we do have some questions. The first is regarding the feedstock. So I think in LIGNICOAT we also use kraft lignin and organosolv lignin as the main feedstock. And one of the questions is if you tested organosolv lignin from wet straw coming from, for example, CIMV France.
Yes, one of our partners in the consortium is CMB. Yes, and we test the withdraw lignin from CMB. In fact, we work a long time until we discarded for the stage 3. We work with CMB withdraw lignin made out of solvolysis, and it gives very good results. But the thing is that in the stage 4, we need bigger quantities, and the biorefineries now, they are not able still to provide big quantities of corn stubble or wheat straw, because it's not their main product. They are working more with hardwood. Is much more easy. So for the stage 4 is not only what is efficient in order of treatment and depolymerization and yields of glycidylation, and also in order to disperse in the materials, is also what is available now, because if we need to pass in states that we are scaling up so much, we need big quantities. I hope that I respond your question.
I think so. Then we have also another one that you presented, how, with some tests, how the BPA compared to the lignin developed in some tests, how do they perform better? So, and the question is about the ecotoxicological test that you mentioned, that you don't observe as much disruption toxicity as BPA, but you do observe some toxicity, and if yes, to what extent? For example,
Sorry,
for
some toxicity in what?
And to what extent? If you observe some disruption or toxicity as BPA, and if you do observe some toxicity, and if yes, to what extent?
You mean with lignin?
Yes.
Yeah, in comparison with BPA.
Yes.
Yes. So we are relatively new in all of this ecotoxicity analysis here at Vito, because we have our Department of Health that is doing very nice work in this kind of ecotoxicological test. But for us, is really new. And we needed to establish a preliminary test that usually they are using to test also this kind of bisphenols, not only bisphenol A, also bisphenol F and bisphenol S. So we are quite new, and we did. I am not an expert. I need to be honest with you. I am not an expert, but I know that our team of health, they did like kind of a preliminary test, and with this endocrine disruption, if I am not wrong, I think that they test one of the receptors, because apparently there is different receptors, and they test with the natural, the one that give the maximum reception. Then they will test with bisphenol A to see how bisphenol A activity is in comparison with the natural one, and then they test the polymerized lignin. The natural one give 100% of activity. What is natural, it gives 100% of activity. Then we have bisphenol A that it have disruption activity because interrupt the activity of this one. And then we have depolymerized lignin that the order of magnitude of this disruption is 100 times or 2 orders of magnitude lower. And this we assume that is because of that lignin is not a well-defined small molecule like bisphenol A. And also the aromatic is modified in ortho position, that this can give more problems to the receptor to get the lignin. So our conclusions is like that the oligomeric part of the lignin, as well as the substitution that it presents in the aromatic in ortho, can affect this less activity for the receptors. But yes, have some activity.
Okay, but they are
but 100
much
times lower.
order of magnitude lower, so it's not completely negligible, but okay, yeah, they thank you.
And we need to say that these are all preliminary tests.
I think we could proceed with the next session. Now we will more focus on flame retardant, additives, and also applied on coatings and composites. So we would have like 15 minutes of presentation from Elvira and then Aitor. Yes.
Okay. So as I was introducing before, what we are doing is developing the 100 bio-based composites for the different sectors. Here we have an initial scheme of, no, it's too fast, an initial scheme of how we are working. In case of Avanzare, we are the responsible of the development of the bio-based flame retardant additives. Arkema is the responsible for the development of fire, smoke, and toxicity retardant development of the bio-based polyamide 11. And Canoe is the responsible of the development of the bio-based fibers we are using, as you are going to see, jute and flax. And then we have partners and use cases, which is leading with the integration and the development of the use cases, CRF Stellantis in case of the automotive sector, Safran in the case of the aircraft, and GeoPanel in the case of the textile and non-woven fabrics for the building sector. So if we start in the case of the flame retardant additives, we are using different bio-based additives containing nitrogen, phosphorus. For example, we are using some of them derived by lignin, which perfectly has explained the process by Mark. And we are also, for example, using chitosan. You can see the sources where we are obtaining the phytic acid, the tannins, or other materials that we are using as flame retardants. As we are going to explain now, we are not using only one material for the flame retardant performance. We are using several of them to achieve a synergistic performance and a synergistic effect to achieve a good performance against the flame. So if we focus, for example, in the some of them that we are obtaining from plant, we are using phytic acid, we are using lignin, and we are also using some tannins as flame retardant. But we are combining all of these flame retardants with other carbon materials that we are producing in-house. Avanzare is producing different types of carbon materials, which is graphene oxide and nanoprelates. So we know that, and it's you can find in the bibliography that the combination of these materials, this carbon material, together some of the bio-based that we already mentioned, is creating a good char, and is creating a stable char, which is a layer helping us to reduce the combustion. We are going to see here some kind of scheme. When the flame reaches the polymer, here in the condensed phase, we have low molecular weight molecules which burns and are comburent for the flames. So what we are doing with the char, with this kind of barrier that we are putting here, is reducing the volatiles that we put to feed the flame. But also we have other two effects, which is reducing the oxygen because can't permeate to the polymer, and also re-radiate the heat because some of the materials that we are putting has high thermal conductivity. So what we are doing is analyzing the char areas, and we see that some of the materials at the beginning that we are putting, some, for example, graphene oxides, have this intense band, which is the band associated to the defects, the graphene oxide moieties, the oxide moieties that we have in the surface of the graphene materials. When we have exposure of the flame, when we see the char, when we characterize, we observe an important decrease in the band because all these oxygen contents has been released during the flame exposure, and we have reduced the material. This is the effects that we can observe, for example, in materials as graphene oxide or graphene oxide modified with chitosan. Until the moment, what we are doing is testing these additives in the polyamide 11, and we are testing according to the UL94. We can see here the basic classification according to the afterglowing time and the combustion time. So the materials that we are combining with the bio-based is some of this graphene oxide and also the nanoplatelets. At Avanzare, we produce these nanoplatelets from a green process in which we are using, if we are considering also the sustainability aspects, we are using solar panels to feed all our resources and our reactors, and we can use natural graphite for do this kind of materials, of the nanoplatelets. And also we can use other feedstock as, for example, wood or other materials that we can use for prepare this kind of carbon materials. In the case of the polyamide 11, Arkema is using a renewable source as castor oil to produce this polyamide 11. And what we are doing now at the moment is providing also other additives to introduce in the polymerization to improve the performance of the polyamide 11. Okay. So here we can see some videos in which we can see the performance of the composite we are testing until the moment. We can see, for example, this one, which is one which contains carbon materials, bio-based flame retardants. And if we compare to the performance of the neat polyamide without any treatment, we observe a significant difference. But the performance that we are achieving until the moment, in the case of the time of after flame exposure, is significantly shorter. It's the time that we need for the UL94. The thing or the aspect that we are improving now is the rheology, because one of the problems of the polyamide is that it's dripping some drops to the cotton, as you can see here, and we have to solve this problem to have a V0 classification according to the needs of the use cases that we are aiming. In this slide, I'm explaining to you that we are also developing flame retardants, bio-based flame retardants for the coating of the fibers that we are using in the composites. So we are using cellulose, which is being developed by Canoe, and other commercial one as jute or hemp. So what we are doing is a layer by layer process in which we are putting some layers on the top of the fibers. It's very important, as you see here in this scheme, the polarity and the pH in which we are working to obtain a very good adhesion of and a very good stability of this layer of the flame retardant that we are putting. So we have developed special additives and a special system to have a good adhesion of the coating into the fiber. If we compare here, this is a treat fiber, okay, and this is a non-treat fiber. So it's really slow. But at the end, you can see that after 10 seconds of the exposure of the flame, in the case of the treat fiber, this is not burning. This is self-extinguished by itself. If we can see how self-extinguished, if we want to see the performance of this one. Yeah, if we compare the non-treat one with the treat, you can see that the flame is not spreading and it's self-extinguished, but it's really slow.
Yes, we can appreciate this, yes.
Yeah, okay. So what we are doing now, it's have some, we are using an airlight process to have the natural fibers in the way that you can see here in the left. So maybe here you can observe that we are working at 1 kilogram scale, and with this airlight system, we are obtaining this kind of mat, which is some of them are used for isolator panels for building. This is the demonstrator, one of the demonstrators that we want to achieve. So the first trials was not performing so good, but now I'm not trying the video because it's too slow, but you can see that we are obtaining now some very good appearance mats with this with these fibers, with the natural fibers, and we are putting the fire retardant treatment here. So the mats are really consolidated, are with good quality, enough quality to make the insulator panels, and we are characterizing the flame retardants performance. And then, of course, we will make with the polyamide 11, we will make the composite for the different use cases. In the case of the aircraft, of course, we are not going to achieve the mechanical performance required with these mats, with these fibers. So in this case, we are using fibers, cellulose fibers, by making prepreg, thermoplastic prepregs, working with polyamide 11 to prepare the structural components. This is what I was explaining before. This is the tapes that we are developing with cellulose and polyamide 11. We will do this kind of weaving, and by thermocompression, we will make the demonstrator for the aircraft sector. So, of course, we will focus in the following years, because this project has started 1 year ago. We are still 2 years and a half to run all these demonstrators. So what we are doing is, of course, the LCA of these thermoplastic bio-based composites with all the inputs from the first work packages. We will do the environmental, economic, and social, of course, and circularity assessment with the prototypes that we are developing. At the moment, we are seeing all the synergy between the carbon materials and the other bio-based flame retardants. We have to modify the rheology and the fluidity to adapt to have a good performance. We are focused for the best synergistic formulations, and we will prepare and test all the properties. Of course, focusing also on the LCC and LCA analysis. And this is more or less the status of the ThermoFire project. You can follow us in the LinkedIn, or you can visit our webpage. I don't know if you have some questions. Really sorry for the videos because it was too much and maybe too slow in the presentation.
Yeah, thank you very much, Elvira. Can you share somewhat more details on the pellets? Oh, okay.
Yeah, at Avanzare we produce what we call platelets. We start from a graphite. Okay, if we think in a graphite like a book with a million of layers, what we do is a mechanical exfoliation of these layers, and we are using a liquid phase exfoliation system. We are not using any solvents but water. So what we are doing by this mechanical exfoliation is expand. It's like if you think in a book, you cut the glue between the layers, and you have separate layers of graphene. More or less, our platelets have between 5 to 10 layers of graphene in an average way. And depending on the process and also on the raw material in which we are starting, we have platelets of 2 microns in the average, 7 microns, or 40 microns. So depending on the applications we are focusing, we can use one of others because the lateral size is really important. For example, here in the flame retardancy performance, if you want to create a chair, a physical barrier to avoid the penetration of the oxygen and the radiation of the heat, you have to create some kind of physical barrier. So we have tested the different lateral sizes, and in some cases, for example, we have seen some effects in the synergies between the smaller and the larger one to create an stable chart. But for example, for radiation of the heat, in the case of the larger one in the lateral size, in this case, for example, what we call plat 40, it's more interesting because it has less defects because the quantity of area regarding the edge is larger. So we have a higher thermal intrinsic conductivity, and the radiation of the heat it's more effective. I don't know if I answer your question. If not, Johan, you can contact me or what you need.
Yeah, I think nowadays there is also an increased focus on graphene-based material, and I know that graphene is kind of more expensive rather than what you're using. So I saw that you're using graphene oxide. I don't know in which form you use it, whether it's in a solution or is a powder form.
Yeah. We have the possibility to do both because we produce the material. So we start from the graphite. In this case, this is not a physical process like in the case of the platelets. We are doing a chemical process. to oxidize the graphite and expand to having graphene oxide. So we can work in water systems, so we can provide it. For example, if we are coating the fibers, which is going to do in a solvent media, this layer by layer system, we can work with this suspension. If not, if we, for example, are feeding an extruder, maybe we need powder, so we have to collect this powder and put it with a polymer or in a matrix or whatever. So we can do both. Initially, yes, the graphene oxide range of prices is higher than the case of the platelets because the system and the process that it's required to produce it. And I think we have the question also from Johan about the chemical modification of these platelets. Yes, we can chemical modify, but typically, in the case of the platelets, we don't have oxygen moieties or other heteroatoms. We have the carbon layer of the graphene. Okay, so typically the chemical modification of these are more non-covalent modifications, not covalent, like in case of the graphene oxide, where we have the oxygen moieties easily reacting with other groups, for example, amino, silanes, or other groups. Can we modify? Yes, but maybe not so easy like in case of graphene oxide.
We can proceed with the next one. So you saw how the first session was more related to bio-resins, and now we go more into the flame retardant part. And now we see also what is being done in LIGNICOAT. So we start with Aitor, please. If you would like to, we see your screen, not in full mode. Okay, now it's perfect.
Thank you, Michele. As commented before, my presentation is LIGNICOAT is now focused on bio additives as fire retardants, but we have some tasks devoted to this. So my presentation is more generic and is more about the principles of fire and how to characterize some tips about coatings, and we will have some example of LIGNICOAT at the end. So why improving the fire performance? As commented by Elvira, most of the materials we use daily are combustible, so we have natural products. We have most of them are organic, so we have composites, we have biocomposites, flammable liquids, thermosets, textiles. So we need to improve the fire performance because there are some risks in case of fire. In case of fire, that is prevent the loss of property and human lives. It is very important that in case of fire, the most important is the human lives. All the standards are focused in preventing the human's life, not the property. It is very important because the designs or the protocols are looking for the safety of the human, no for the property. And there is, of course, a fire regulation. If you are going to develop one of these products, you need to fulfill the fire regulation that are more and more requirements and more difficult to fulfill. Of course, nowadays there are very important other regulations that are the chemicals and other regulations because the fire retardant are chemicals and most of them are in the focus of REACH or roads or other registration and regulation protocols. That is very important because we need continuous advances and developments in this field. There are a lot of standards. In the case of fire, it is very important the fire scenario that depends a lot of the load of fire and where is this fire. In case of construction, you have a very high load of fire and you have limited time to evacuate the building. So the standards in construction are very high, are very demands. In transport, in some cases, you have very good evacuation, very short evacuation time, so the requirements are not so strict. And in the case of plastic, like electronic and electric devices or cables, you want to prevent the ignition of this material, or that these materials does not promote the fire growth. So these are some examples. It is very important the selection of the application, because it depends a lot the method for the fireproofing to be selected as a function of the application. In case of fire, we have different stages of the fire. Sorry. In case of fire, we have the ignition, the starting of the fire. The materials start to burn and reach one point that is now the flashover, that all the materials burn simultaneously, and you have a developed fire. You have a very high temperature, and as the combustible is consumed, you have a decay. This is very important because for the materials, there is different nomenclature or names. That is reaction to fire, that is the material contribute to the fire, and resistant to fire, that is a material need to maintain some performance in case of fire. This is very important because most of the materials, organic materials, we talk about reaction to fire, not about fire resistance. Okay, for example, in case of construction, in building codes, in regulations in Europe, we have a standard that is 13501 that is regulating the requirement that we need for a materials that is going to be in a building. For the selection of the test, for example, there was in the past a lot of studies calculating what is the typical flux or the typical heat that is applied to materials that could be in a ceiling, in a walls, and in a floor. In case of fire, you have more temperature here, so the radiation is different from the floor. So in case of construction, for example, there is different methods for classification the flooring materials for ceilings and walls. So you could have a good material for floor that could not pass the standards of the requirements for the walls and ceiling. This is also very important. What is the final application? As commented before. Other important topic is the active and passive in case of fire, because the active is the typical water sprinklers. In case you have a fire, you have a mitigation method that is active. But now we are talking about passive, that we are acting in the material, in the design of the material, creating physical barriers, as commented by Elvira, some bulk application of fire retardant that can create a layer to protect this material, cementitious materials, gypsum, of course, organic coatings. I'm going not to explain in detail the principle of fire, the combustible cycle, because it has been explained by Elvira, but this is the phenomenon. You have heat, the material starts to decompose, generate combustible material, generate radicals, a very exothermic reaction that create the flame. This flame affect also the polymer or the material that start also to decompose, and you are creating a char or a solid material, and you have the gas phase and the condensate phase. So in case of fire or flame retardancy, you want to affect here the gas phase is the most efficient way for suppression of the ignition, or to release less heat, or to avoid the formation of the flame. You can add also in the condensate phase. You can use materials that promote sharing, or you can use barriers that inhibit the heat of the consume of oxygen. In case of fire, in case of combustion, you have different outputs. You have heat. When there is the fire propagation, you have a lot of nomenclature, that is the inflammability, heat release, temperature of ignition, time to ignition. But you have also some solids, because you can there is so dark that you can evacuate, and is in some cases is worse than the exposure to fire. So this is a smoke density parameter. But you have, for example, in Rightwell or in other standards in vehicles, you have to declare the toxicity, because this species can be incapacitation, can promote incapacitation or aphasia. So these three phenomena are very important. What about the mechanism of the fire retardants? As commented, there are some fire retardant that are in the vapor phase, that is the very well-known halogenated compounds that are the most efficient fire retardants, because release radicals that react with the radicals in the gas phase and avoid the flames, inhibition of the flames, and decrease the temperature. So these are very important in the last year in the previous fire technologies. They were very important, but they are toxic. They produce toxic gases and they are inherent toxic. So the tendency in fire retardancy is to avoid the use of halogenated compounds, but there are some cases that I'll still use it. Nitrogen-containing compounds, the mechanism is to release nitrogen. They have nitrogen in the structure, so with the heat, they release inert gas that is nitrogen and dilute the concentration of the flammable substance in the gas phase. So it's a other mechanism, but this is not so effective. So you need high concentration of this material. One of the most famous is melamine, that also promote char formation. Phosphorus-containing compounds, that is the most used alternative for halogenated compounds in the current, in the present. And they have two effects. The most known is the promotion of phosphoric acid by the composition, and the promotion of the char in the solid part of the combustion, and it is not toxic. There are some species of phosphorus that promote also radicals that act in the gas phase. In the case of inorganic compounds, like commented by Elvira, there are some inorganic compounds that capture the heat of the flame, so dilutes and cool the material for this flame, for this heat, and also they use to release water when they have water of hydration water, and they release the water, so dilute also the gas in the combustion. There are some examples: aluminium, magnesium, boron, antimony oxide. Okay, but what is the advantage of coatings? As commented, in case of composites, you need a lot of quantity of fire retardants, 20-30% in some cases, depending on the application. So it have an important impact in the mechanical performance of the materials. In most of the cases, you decrease a lot the performance of this material. So the use of coatings is not only economical solution and also a lightweight solution, that you are not increasing a lot the weight of the material, but you are promoting a very efficient physical barrier for the material. It is also a aesthetic solution. For example, in case of wood is very important, because the aesthetic of wood is important for the application. So you are looking for transparent coatings, and it's easy to apply it, because you have the material and you can spray, you can brushing, you can apply by roller. Okay, and it's compatible, of course, with different substrates. There is a special technology for fireproofing, that is the intumescence systems, that is more focus on fire resistant because it's a very, very effective method for insulation of the material. So in case of fire resistant, that we are talking about 1,000 degrees, 1,200 degrees. That is a very high temperature. You need this kind of mechanisms if you want to protect the metal or the substrate. So the principle is the formation of a expanded porous carbonaceous layer, and you maintain you obtain a non-flammable insulation, physical and thermal barrier. So sometimes you have here a picture. You have a very, very thin layer that you can obtain 100 times thick foam to protect your material. It used to be 3 components in these formulations that are acid source, carbon source, and also blow-in agents. Acid source used to be a phosphoric acid, for example, or phosphates, sorry. And carbon source, you have different polyols and carbon-rich polyhydric compounds. In the case of blow-in agent, you release nitrogen typically, and as commented, melamine is one of the most used. What are currently the challenge to solve? As commented there, most of these fire retardants are toxic, halogenated compounds, antimony-based compounds, boron-based compounds are also because of lixiviation of boron. And also melamine currently is an important topic because it's in the focus of legislation. Other important issue is the water sensitivity, because most of these fire retardants are hygroscopic, so capture water. So you have lixiviation, you have less performance, you have reducing the increase. You are reducing the service life of these materials. In tungsten transparent systems, because in tungsten, the cocktail commented before, you need a quite important amount of material, so used to be not transparent, so it's a quite challenge. And also important challenge is the sustainable coatings, the recyclable systems, and also use of bio-based resins and additives. So in the case of LIGNICOAT, we decided to prepare some fire retardants in order to use in these coatings, produce these fire retardants based on the lignin. As the main topic of the project is lignin, we decided to prepare active fire retardant based on lignin. Tecnalia has a patent for production of polyols from lignin, so we started with these polyols, and we use a Williamson reaction in basic conditions in order to obtain a phosphorylated lignin polyols. It is important that it's a liquid, not a solid, so we can manage better in this kind of applications in coatings. We prepared some, these developments are currently ongoing, but we prepare in different formulations. We use a reference formulation based of a developed, as commented in my introduction, a polyurethane alkyd system dispersion based on lignin. And we have other for comparison, a typical system based on APP, that is a commercial ammonium polyphosphate, that is a commercial fire retardant. And we prepare the lignin phosphate as additive, but in this case we have problems, and we only reach 8% of additive, so we just reach 0.3% of phosphorus, that is very low. And we decided to move in order to increase the lignin content and also the fire retardant content. We move for a 2 component system using the lignin polyol, phosphorylated lignin polyol, as a polyol in a typical polyurethane system mixture with isocyanate. And we also prepare a product with 10% of APP. Here you can see the conic calorimeter curves that are the Claudio is going to explain later more about these techniques of characterization, about conic calorimeter and the other characterization methods. But this is the most used in research in fire. So you can see in black the substrate that is a good base particle bar. This is the profile that starts with the ignition, release heat, and they have a second ignition. In the case of biopolyurethane without fire retardant, you see that the coating worse the performance because it's ignitable, release some heat before the starting of the composition of the good. And when we use as an additive, as commented, just 0.3 phosphorus, we improve this performance. We are close to the material, to the particle boil substrate, in reducing the total heat release because we are under the curve of the substrate, but it's not enough. We obtain good result, but it's not enough. If we move to the system, if we move to only ammonium polyphosphate, we see that we decrease a lot the ignition. We create a barrier that protects, but not enough to avoid ignition of the substrate. So we reproduce the curve of the substrate in yellow. With the use of 2.7% of phosphorus in the LPO, phosphorylated LPO, we see the peak similar to the previous, to the bio-based formulation, but we decrease significantly the combustion of the material. But the most interesting result is the synergy effect between 10%, just 10%, and the LPO. So we have a low peak, an important barrier. We have reduced it a lot, more than 200 seconds, the combustion of the material, and start the combustion, but with a very low heat and very low total heat release during the combustion. So this is a good result. We are reducing 5% of APP using a less amount of a bio-based lignin, phosphorylated lignin. So this is all from my part. We are currently working in the project in the increase of the phosphorus content and in the increase of the LPO in the final formulation of the coating.
Thank you, Edgar. I think it was a very yet global and comprehensive presentation. So we have, I think, the participants have a better view on what we mean with flame retardancy and where we are acting. So in the passive form. Yeah, I think also that most of these we will go more in detail with the next session with Saul and Claudio, where we will have more details about what we are doing in this term. I can ask a little question. Regarding the last slide for the particle board combustion test, in that case there was the benchmark, so no coatings were applied in that case.
No, it's just the substrate.
Okay.
You have in the standard, in construction standard, you have a standard substrate that you can use, because in the case of wood, for example, if you are going to develop a coating, you need to validate in all the types of wood, hardwood, softwood, pine, spruce, all. And all the colors you have in the formulation. So there is a important cost, an important campaign for certification. So there is a standard that use a standardized substrates that if you demonstrate that in these substrates your coating is effective, you can extrapolate to this range of densities of good. So we use this particle bar as a reference.
Okay. Okay, thanks, Aidor. Okay, I think I can welcome you back. I hope you had a nice break. So now we will proceed with our presentation, with our sessions. We have indeed application with Saulo from Barpimo and Claudio from Iris, and then we will conclude with an open discussion. So I welcome Saulo to present, so feel free to share your screen. Perfect.
Okay, thank you, Michele.
Thank you.
Okay, I appreciate very much the invitation to present today our research about alkyd resin based on lignin polyacids. We part of this consortium, and we today will present our develops made of using lignin in alkyd resins. And Barpimo is a paint producer, but also we produce our own resins. So this is why I will present this presentation about alkyd resins. So alkyd resins are modified polyester resin produced by the condensation reaction from fatty acids, carboxylic and polyalcohols. And alkyd resins are the most versatile synthetic resin in the market in nowadays. So their adaptivity, cost effectiveness, and ability to be customized for specific applications further than enhance their value as a versatile resin in the world of coating paint. So alkyd resin is very, very versatile material for the coating industries. And here I would like to share with you some information about the alkyd resin market. The major consumer of alkyd resin is North America, followed by Europe, and then Asia, and Central and South America, and then Middle East and Africa. The product outlook, alkyd resins are divided in three major different types. Is a short alkyd resin, medium alkyd resin, and long alkyd resin. So this is related to the oil content or fatty acid content in alkyds. So short alkyds, it's a short or a low content oil content. Medium alkyd is medium oil content in alkyds, and long alkyds, it's more than 50% of formulation is about oil. So the oil fatty acid is a great contribution of the properties in the resins, especially when we talk about do-yourself coatings, for example. So air dry enamels. So it's very, very useful in the do-yourself markets. In a case of formulation outlook, we have a high solids alkyd, waterborne alkyds, modifying haldex, solvent-borne coatings, and others. So today in the market, waterborne coating alkyds is one of the most resins demanded right now, doing all the VOCs issues and other demanded markets. So waterborne alkyds now, it's one of the most developed type of alkyds right now. And the end use outlook is the sectors in automotive sector, construction sector, electrical, electronic, aerospace, and other uses. So why use lignin in alkyd resins? So as we see previously, lignin is abundant and renewable resource, offers a great potential for functional material coatings, and underutilized byproducts of the paper and biofuel industry. So as we see previously, most of the lignin is used to burn for use as a biofuel. So today we will show to you a revalorization that is possible using craft lignin in coatings. Another things that we consider as we use lignin act as a natural cross-linking resin. So as we saw today, lignin has a lot of carboxyl hydroxy groups, so this is make possible that we use lignin and not this material stay in a molecule not attached to anything, but as lignin has a lot of functional groups, this is make possible that lignin can be attached in the molecule of the resin. So another possibility is to reduce dependency on fossil fuels. And of course, in this development, we replace partially polyols and polyacids. Today we'll focus more in polyacids, but it will be possible also to replace polyols. So in our case, in this study, we have used a low molecular weight fractionated lignin provided by VVT. So we make the study, and VVT has provided several types of low molecular, medium molecular size lignin fractionated, and this case, what it works, it was low molecular weight fractionated lignin. So we attached this in the alkyd molecule, and was successfully achieved the alkyd formulation. So here we have the classical process diagram of the alkyd resin production. So we have the reactor chart, we chart the polyols, polyacids, and we have the esterification process, water extraction, the polymer growth, and then the dilution or the emulsification in the case of waterborne alkyd resins, and then filtration and packaging. In this case, the use of lignin help us to reduce the water waste treatment as a huge molecule. As you know, in the case of the esterification process, we have a water provided by polyacids like phthalic acid or benzoic acid or isophthalic acid or from the fatty acid acids. As we use lignin as a huge molecule, we reduce also this water extraction. So it's also in this point of view of process also helpful for reduce the waste during the process. In the beginning, we start the optimization of the alkyd resin formulation. So we tried 3 different percentages of lignin because, of course, we didn't know how it was performing. So we try the modification with the 15%, with a 20%, and with a 25%. So with these 3 modifications a month, we found these results. So with a 15%, we have a dry time after curing of 144 minutes, attack-free dry time with the versus hardeners with 130 seconds and a gloss with 93. And with the 20%, we saw an increase of a dry time at attack-free minutes in 152 minutes. The harder versus decrease a little bit, the gloss, well, a little bit more. And we had modification with 25%. We saw a dry time attack-free more than 200 minutes. That's for this type of resins that we are looking for. 25% was not suitable for this type of application. So, and then after we decided, we choose to modify our formulation, focusing 15%. And this was the proposed formulation. So we introduced 15% of lignin polyacid content. The oil content of the alkyd was a short oil content, 38%. So with a mix of a soybean fatty acid and DCO fatty acid. This combination is because we have achieved better properties. And the estimated bio-based raw material content, in this case, it was 50%. So we could increase if we decided to use other bio-resources from polymers. For example, we know that there's a penteritritol from bio-resources and other polyacids also from bio-resources, but we decided to focus on a classic formulation. And we established hydrox excess 31%, acid number 40-45 milligrams kg, the alkyd constant 1.04 kappa, and the functionality 2.08. As a result, we obtain an alkyd resin with a 40.42 solid content, 38 oil content, color dark brown, lignin polyacid content 50%, a viscosity 600 CPS at 25 degrees, and the pH 8.2, and the bio-based content about 51%. So here is the fluid of the resin. The resin immersed in water. So as you can see, it's something very liquid. The color is a great challenge in this case, but we be able to find some specific applications. So here is also, we share with you the molecular weight distribution analysis by GPC. So as you can see, the standard, we establish a standard alkyd resin as a pattern, and the lignin modified is this version with lignin provided by VVT. So as you can see, with a 15%, there's no great difference between the two resins. So we see very similar, and it's a good thing. So with a 50%, we can consider there's no big difference, and it's something that is suitable for use. After that, we started characterization, set to touch time, dust-free time, touch-free time, and dry-through time. So as you can see, we have a little bit difference between alkyd standard, lignin modified, but it's something that is assumed. It's not so, it's not bad. Gloss is something also that we see that is very similar, and the hardness a little bit less, but it's also assumed for our application. Well, and here we have another video in the production of the alkyd. As you can see, that the reactor, you have performance, no gelling or particle dissolved, or sometimes some raw materials cause a lot of foam. So in this case, the performance of a lignin in a reactor was correct. And then we performed bake enamel based on alkyd lignin resin. In Barpimo, we formulate coatings for bake enamel, and this we have the standard characteristics for our standard paint, and then formulate with the new resin based on lignin. So the viscosity a little bit higher with the lignin modification, and the pH similar, solid is similar. VOC, of course, as we introduce new raw materials, we'll be able to achieve a very reduced VOC. In this case, you can ask, so why you achieve only 10.8% of bio content? This type of coating, it's a high filler content, so it's a lot of mineral fillers in the formulations. So, and these fillers, they're not considered bio. So this is why we have a very low content in bio raw materials in the formulation. Not because we not be able to introduce more bio content, but it's because the type of formulation. But for this type of formulation, 10.8%, it's quite good. The gloss we be able to achieve a little higher. It's a good thing. Physical tests were okay. As here we talk about salt spray test, and well, Persos hardness similar. And the problem was with the humid test, so we not be able to achieve at least 100 hours. So it's the only test that we not be able to pass through. So, but this is the case that we can work and improve the characteristics. So this is the first intent, the first prototype. So, but we assume that these results are quite good for this type of applications, and we be able to improve. As you can see, the limitation of the resin is the color, so we decided to formulate a black one paint. But of course, as this limitation also brings other possibilities, but we see a lot of possibilities. So the conclusion and takeaways from this new development: lignin present a promised alternative for enhancing sustainability and in alkyd production. Craft lignin could be a real alternative to aromatic polyacids. So it's we see here today it's something feasible. The color of the resin could be a limitation, but also opportunity for new applications. And we, of course, require further research for industrial scale-up. And the next step is to develop a 95% bio-based alkyd resin. Of course, we can replace all the polyols, all the polyacids by bio-based materials. So this is what we have until now. And thank you for your attention. And you can reach me by mail or everything. So, and I appreciate to be here with you. Thank you.
In the meanwhile, I can have a question. So I think it's a very positive that we can reach even. I mean, it's planned also to substitute some components in order to reach like almost fully 100% bio-based resins, bio-based alkyd resins. Instead, I saw from the lignin components, so how much fractionated lignin we put. I think it was selected a 15%. Is this 15% like something that we cannot go further, or there are some space, some room for improvement here?
Yeah, I believe that we have a space for new develops here. Of course, this was the first intent. So I think as with VVT, for example, be able to reduce the molecular weight of the craft lignin. So I think a lot of possibilities is possible here. So it depends, of course. We have a lot. Some variables, the lignin molecular weight, we have, of course, alkyd resin formulation, it's an infinite possibility. So 15% is just the beginning, I believe. I think in the future we'll be able to introduce 20, 25%. So, but of course, this is the first one.
Okay, thanks. We have also a question from the audience. They are asking you, when will it be possible to see a more transparent lignin-based resin?
Oh, this is a good question. Yeah, the color of the resin, it's a great challenge. So it's a big issue. So will depend of the craft lignin purification. I believe we'll not be able to improve so much, but I think something will be possible. But we need to assume that the lignin is it's a brown material. So yeah, it's something that we have to assume. So it's a natural material and is a characteristic of material. So maybe in the future would be VVT will be able to produce a low color, but it depends of the origin of material. As we saw in the beginning, for example, sugar cane could be a possibility. We don't know the color, but sugar cane could have a low color in comparison with this type of lignin, because we using a specific type. So we need to consider that lignin have several different types of lignins and colors. So it's a small word about when we talk about colors. But of course, it will depend on the origin of material, purification, and but in my knowledge, I assume that the brown color is a characteristic of the lignin.
It is a point that comes very often, and I think also in some application it can maybe even enhance having a brownish, yellowish color. Okay, so I welcome Claudio from Iris Coatings.
Good morning, everybody. And thank you for hanging on till the last presentation in the morning. Can you see my screen and hear my voice?
Yes, we can hear you, we can see you. Okay, now it's also full screen. So yeah, always the best at the end, no?
We will see. I would like to talk a little about lignin-based flame retardant coatings. And this was a part of the LIGNICOAT project. If you allow me to start from the conclusions, indeed, the project is almost at the end. We are about to close it in a month or so. And in the last 2 years of the project, we coatings guys have been working on the materials that came upstream from treatment of lignin in different ways. And I can say we had given ourselves in the specific work package devoted to flame retardant coatings at the target to create 2 types of flame retardant coatings, and we achieved that. We went through some ideas and work, and at the end, we basically developed a technology which is based on the use of lignin as a polyol itself to make polyurethanes. I will give you some more details. And we have tested the products that we have made for all the properties that are needed to be a good coating. That means film forming, the ability to spread on a surface, but also not to flow when the surface is vertical. And once they are spread on a surface and create a film, this film needs to cure or dry, that means chemically or physically. And once it is cured, it needs to have a proper hardness, adhesion to the substrate, resistance to abrasion or to chemicals and other things. And as a consequence of all this, it also needs to keep these properties during time, so have a proper resistance to aging, weathering, if it is exposed to weather outdoors or to moisture. And there is a very large number of properties that you can test, but we have tested quite some of them, at least those that were interesting to our field of application, and we measured good results. So we are satisfied with that. There is one problem that has been mentioned by the colleagues before, I think all of them, that damned lignin is black. It is black, and even if you treat it or change it or you add it to something else, the dark color will always remain. And this is kind of a limitation, definitely. A little more in detail what we have done, what is the most interesting result that I can see. We have created lignin-based polyurethanes with fire retardant performance. That was our target. And we have done it starting from lignin because of a number of reasons, because we have been invited to this project in the first instance, because lignin is an interesting potential raw material, abundant, whatever. But the important thing to us is that lignin is the major or the only important source of bioaromatics. And we coatings people like aromatics. Like Christine said before, if you use aromatic building blocks, you expect to have a better hardness, chemical resistance, and generally better mechanical properties of the film that will have an effect on its durability and all the application characteristics. And this is one point. But the other point to us fire people, you can discover that lignin in particular has a good thermal stability. For example, by running the thermal analysis, TGA, for example, and comparing different types of lignins with conventional polyols, you discover that the thermal stability of lignin is higher than, of course, than aliphatic polyols. And this gives us a hope that the final product will be inherently more resistant to the flames. Why polyurethanes at the end? We went through some work and we came to this idea at the end. Lignin has quite a large number of auxiliary groups. You have seen the molecule before. This polyol here in my picture, of course, is not lignin. What you need to make a polyurethane is at least difunctional isocyanate, so a molecule including two NCO groups, and the molecule including at least two OH. And the reaction of this will give the urethane link and a molecule more or less of this kind. Well, lignin is rich in OH, and we can expect it to perform this function. It's not a new idea, sincerely speaking. I'd like to quote someone here, but there's more scientists who have been working on that, particularly people at the Politecnico di Milano in the group of Stefano Turri. Particularly Chiara Allegretti has been working on making coatings and resins in this through this reaction. I see an interesting point in this polyurethanes, because the fact that we have been able to make polyurethanes can probably extend the field of application of our results to a larger market than we are focusing on. I'm not a market researcher, so I just grabbed a couple of numbers from the web just to show you that the paint and coating market is something around $200 billion in value, expected to increase. And the fire protection market, all of it, is just a tiny fraction of it. This is the reason why we are there, by the way, because we like to be in a niche and to make special products for the fire protection market. But as a matter of fact, it is not as big. But in general, in the coatings market, polyurethanes have a large role. General industry use a lot of polyurethanes. Architectural industry to some extent, the automotive, marine, protective, all of these sectors use quite a large amount of polyurethanes. Some of them are very demanding in terms of quality and performance, like the automotive. Don't expect to see them using lignin derivatives so soon, but there are a large number of sectors where polyurethane can be used. And the polyurethane market is more or less 10% of the paint and coatings market. So think of it as a further downstream of the LIGNICOAT project. Some should think further of using lignin as a polyol to make polyurethanes. Having said that, and I've given you an overview at the beginning, where it seemed very straightforward and simple how we reached this idea to make polyurethanes by direct reaction with polyisocyanate. It is not so in practice. We went through a long journey. We have been using different types of lignin derivatives, both soluble fractions obtained by solubility fractionation at VTT and other types obtained by depolymerization at VITO. In all cases, we have got as raw material for our studies this low molecular weight lignin, and at the beginning, we actually got resins that were made through polyols and polyacid derived from lignin, incorporated into a resin that we were expected to use as a binder, single component or two component. Only in a later step, we learned that we were able to directly react low molecular weight lignin with isocyanates in a two-pack system and to obtain coatings in that way. Two-pack system means that lignin is included in one of the components and the isocyanate in the other, and you have two drums that will be mixed just before application, and the reaction occurs during application, and this is giving a particularly high characteristic of the coating. We have used as a reference throughout all our work two benchmarks. These are products that are currently on the market and can be considered as reasonably representing the two main types of flame retardant coatings. One is for the application on floors. The classification BFL means that they are specifically for that. Aitor has given an interesting outlook at the beginning how the market works and is regulated in this respect. The second product, chart 17, is for general purpose application. That means, referring to the slide of Aitor, it can be used both on floor, walls, ceiling, wherever. And this BS1 classification is much more demanding in terms of reaction to fire. So having considered these two benchmarks, we went through developing our own new formulations and testing them for a number of parameters. As I mentioned before, we need to have all these properties to have something that we can consider a good coating material. So we made quite a number of specimens at the beginning for physical testing, then for a simple internal method for reaction to fire testing to appreciate whether we were able to protect the substrate and to which extent, and to observe whether we had charring to some extent or no charring or whatever. And the results, the better products from these screening tests were brought to the cone calorimeter. The cone calorimeter is a fantastic tool for fire scientists because it allows to examine how the fire grows in very controlled conditions. In particular, this is the cone itself, and the name comes from the fact that you have a kind of heater, an electric heater in the shape of a cone, and this is giving a very uniform heat flow to the surface. So you can burn a sample, you can extract smokes in the process, you analyze the smokes. Generally, there is no temperature measurement here, so what you measure is not the real heat flux, but it's the theoretical heat developed by fire, calculated from chemical analysis. This is a typical result. I don't have shown another before, so I will only say that with this results, you can see, for example, this sample is lignin-based. Its combustion starts later, so it's better than the other specimens in that respect. The heat release is also smaller than this one, for example. You normally observe a behavior like this. You have a flash at the beginning, then the combustion goes slower, then you have a stronger combustion later on. And all in all the area under this curve is the total heat release. The smaller it is, the better the result will be. This charity is our benchmark. All in all, you see that this lignin-based material is kind of doing better, even better than a product that is now a market reference. Though the cone calorimeter is an ISO standard, the regulators basically don't like it, or the regulators like to see a bigger fire scenario because fire is a very complex situation, and they like to see something closer to the real life. So once you have studied your materials in the cone, you generally want to test them to have an official approval of fire performance, and you do it in two ways. For floors, you will use this equipment. This is also an ISO standard. It's a radiant panel radiating heat on a surface of a sample, which is put horizontal and receives the heat flux from above. The heat flux starts from about 11 kilowatt per meter square here, and then it decreases because of the angle of exposure. So in general, this is not a very demanding test as far as flame retardancy is concerned, and we consider it quite easy to pass. As a matter of fact, we have tested our products against it, and for all of the materials that we have chosen, we have passed the BFLS1, which is the best class you can aim at. Nobody has been speaking about the Euro classification system, but I think most of you are familiar with it. Classes are named from A to B, C, and so on. So B is not the best all in all, but it's the best you can achieve with this kind of material, because A classes are only for truly non-combustible materials. So this is an excellent result. And interestingly, one of these specimens was a sample including no added flame retardant. The fire performance was obtained only by the inherent thermal stability of lignin. And well, this is very good in my view. But this is not the most difficult thing to achieve, because we need to have also another material, or a material that is able to pass the test for floors and also for walls and ceilings. And we believe you normally need an intumescent system to do that. Aitor explained what an intumescent system is, what components are needed. And here comes another idea. A carbonific, what Aitor called the carbon source, is normally a material rich in hydroxyl groups. The most common is pentaerythritol, but also starch or sugars have been proposed in literature. And lignin has a lot of hydroxyl groups. So can it work as a carbonific, as a carbon source? There are some hints in the literature that it might do so. We have done a number of tests. Actually, lignin alone can give some degree of expansion, but not much. But if you add some additional standard carbonific or some blowing agents, then you can achieve an interesting expansion ratio, up to 40-something%. Aitor said that you can have expansion in tumescent coatings up to 100 times. This is true. We have commercial products that do that, but this expansion is very good and probably good enough to get a good reaction to fire for our purpose. So we went to the single burning item test. This is the difficult thing to pass because the heat flux here is bigger, is 40-50 kilowatt per meter square in this area where the burner is. Again, it's another type of test where you indirectly measure the combustion parameters. The walls are coated with our product. The substrate is a flammable material. As I already said, it's a particle board that by standard we consider as the universal substrate representing all types of wood. And well, we run the test and we see the results. These results here are not enough for the classification in the Euro classes, but these are the important ones. And well, all these results are enough to pass a BS1 D0 class. Additional tests have been also done, and finally, we can claim that our material has been classified as BS1 D0. It is a very good result. So, well, we are happy. We have obtained products that reach the targets that we have chosen at the beginning pretty well in terms of reaction to fire. We feel fine. We have also found a way to use isocyanates as a directly curing agent to lignin. So to prepare a two-pack coating directly using lignin and isocyanates. Some may say now that isocyanates doesn't make us very happy on a green perspective and on an environmental point of view. Sure, they are a dangerous chemical. They are the subject of the diisocyanate directive that puts limitations on them and consider them as dangerous, to be treated as dangerous in the workplace and so on. But there's a good news. The isocyanates that we are using and that most paint companies are using nowadays are large molecules, polymers or adducts with a high molecular weight. And these are not as dangerous as the small molecular weights. The materials that we use have a diisocyanate content lower than 0.1% that allow us to classify them as less dangerous in terms of labeling, REACH, CLP, and the diisocyanate directives. So all in all, these products are quite relatively environmentally safe and safe on the perspective of health at the workplace. The other numbers make us happy. We have reached a bio content of up to 50% due to the fact that we have used lignin, that is completely bio origin, and we have also used the polyisocyanates that are partly bio-based, and we have reached a lignin content in some of our materials that are up to 30%. That makes the lignin content of the product up to 30%. So again, this makes us very happy. You can see pictures of the materials that we have done. Some of them don't look that bad. Some of them are, well, a bit dark or not really as transparent as we wanted. Basically, those that can pass the simpler reaction to fire test allow us to use less additives, to use a smaller amount of lignin, to use different conditions, and they look better. Those that need higher fire performance needs more additive, and in general, they don't look as nice on an aesthetic point of view. All these points will have an effect on the final market acceptance. At the end, we can state that we have products that, in a way, are kind of close to the market, and we have to ask ourselves what is needed for a full market acceptance in the future, or for them to gain a market share. First of all, they need to be good coatings, and they are, even more than we expected, especially the ones that we have done by direct cross-linking of lignin are very hard in personal scale, resistance to wear and tear, and to weathering, so that they look pretty good to me in that respect. And they give us a good hope that they can be good coatings in terms of coatings performance. I think for sure we have proved that in our field, reaction to flame retardant coatings. And if we want, someone will want to enlarge the application in the future to other type of polyurethane coatings, I'm thinking of flooring, I'm thinking of machinery, industrial coatings, and more. Probably they will find a good starting point. And of course, they will have to test further for these technical parameters. The second thing is, what price will these products have? I have no idea. I'm thinking that the market would be able, or should be able, to pay a little higher price because the material has sustainable characteristics. This is normally true for other products, but this is only true to a small extent. People will not be willing to pay double just because it is green, unfortunately. So we will have to see what the price will be. The good thing is, lignin comes from a very cheap source. It's basically a wastage of the pulp and paper industry. So the raw material upstream is cheap. We don't know what the processing costs will be to obtain the lignin derivative grades that we need. So actually, this is a so-and-so question mark. We don't know about this point, or I don't know at least. The third point is, when will they be commercially available? I'm pretty sure they will be sooner or later, maybe sooner than later, but I don't know exactly when. And what we need is what I called resin grade lignin, so depolymerized or fractionated in a way that they have a clear profile of characteristics, a constancy of this characteristic, a factory production control that guarantees that they are always with the same properties, and this is something that has to be created on an industrial scale. The pilot plants that we have seen at Vito and VTT are very promising and very interesting in this respect, but still we have to see what will be the final step to the industrialization. And the last point, where I've put a double red question mark, color is a problem. The damn stuff is dark. The more lignin you are able to put into it, the darker it is. So this is going to be a problem. In our specific field, application on wood, we have been thinking that actually products for wood are normally colored in a color that resembles natural wood. And the color of lignin in this respect is nice. It's the color of wood at the end, because it's the major part of it, bringing the color to it, because cellulose is basically white. So these are, I created kind of a palette, but it's nothing commercial at the moment. These are colors that we have obtained for our specimens, and this is something that I've taken from the web. It's a typical color palette for wood stains on the marketplace. So for the application of wood, we can think that to some extent we can create colors that are a constraint. Not everybody will be happy, but there can be a market for it. If we go to other applications, this will affect everything. If you think of many colors, you can only think of shades of gray, not full high strength colors. This will affect more or less everything. Importantly, I have to mention all the paint industry now goes through a color making industry that is based on tinting systems. That means we work by basic materials that have no color. Then we have colorant or colorant pastes, and this is done on the basis of mathematical modeling through the Kubel-Kamunck equation that involves measuring all these materials by spectrophotometry and creating a system where all these parts can be mixed to obtain a final color. And this is done even in the shop at the request of Lady Maria for 1 single kilogram. Well, all this system is not going to work if you have something as a basic material that is very dark. So this is the major limitation that I still see, and I'm worried because this limitation is probably there to stay. And this is all I wanted to say. I want to thank you for listening to me and for your attention, and I want to say that I'm at disposal. This is my direct contact in Iris Coatings, or you can contact Michele or the LIGNICOAT project. I will be happy to continue talking about this even in the future. Thank you very much for your time. I stop sharing.
Yeah, thanks, Claudio. Very insightful presentation and also very insightful thoughts that will probably also, when some of these thoughts are some of the topic that we will also discuss in the roundtable. Maybe I can ask a question. So if there are no one, you said that Iris Coatings actually figured out that during the LIGNICOAT project, you tested various ways to produce polyurethane resins, and you found out that actually you could go directly from the fractionated, the polymerized lignin. How it came, this intuition? Was something already planned, or you just tested out and see if it works?
I think I mostly have to thank Chiara Allegretti, whom I also already mentioned in one of the initial slides. We were talking about LIGNICOAT, like I did in many instances when I had the opportunity to join workshops or exhibitions or whatever. And she said, I've been doing that before. And I said, what do you mean? I was doing my PhD thesis, and the idea was to go from lignin to coatings. And I realized my time of 3 years was probably too short to go through intermediates, resins, and many other things. So I decided to try and cross-link lignin directly because there's plenty of other hydroxyl groups. So she actually gave me the idea. I've read the literature that she has written after her PhD, and I've quoted one, but there are more on the web. They probably did not go to any practical application or to a scale larger than few grams. We have probably extended the concept to a larger scale, and we were lucky to have some isocyanates, polyisocyanates that worked, because we have tested a few and not all of them were working. A few of them had the proper reactivity and characteristics. So this is the way we did. Actually, I've put some highlight on this particular result, but we have also obtained coatings in the way that was planned at the beginning, so creating a basic resin that with which we could make a single component coating that is much easier to use and much more suitable to the consumer market, for example. That coating was also made in a waterborne version, while for the two component, that one that I like most for the performance results that we obtained, but we can obtain it only in a solvent-borne version. We also have a waterborne version, but the results are not as good. So we need a solvent to do that. And that means you have some VOC being released in the application process and some drawbacks. With the time that I had, I could only summarize some basic results, but there's really quite a lot.
Nice. Thanks, Claudio. I can invite all the speakers for our last session and also the participants. So here the idea is that we go through some questions. So we have two ways, because usually I know that with this interactive tool, we usually get stuck. So there are two ways. You can either vote directly from the teams or by scanning the code. And we will see the live results. So we will have four main questions. The first will be about the benefits that you envision about these bio-based materials or bio-based additives, coatings, whatever you saw today, and resins. Then we will have another question on barriers. So for each question, you will have multiple choice that you can select. So benefits, barriers, and then we have policies, what policymakers should do in order to speed up the adoption of this bio-based material. And then we have possible future scenarios. So let's see if we can. So I will first share the screen with the code. So you should be able to scan it even from your phone. And I will also start with the first question. So you should be able also from Teams directly to see it in the chat or somewhere. I think it should be in the chat. So you can either go by scanning the code online and submit the responses to this, or do it even from Teams. So, okay, seems that something is coming in. The question is about what do you see as the main benefits of the bio-based materials, so the bio-resins, the bio-coatings, and the additives that we saw. And you can select all of these possible answers that we have here. So we do have environmental sustainability, innovation potential, compliance with regulations, and performance and cost effectiveness, which it seems that it's kind of stable. It's kind of overwhelming the consensus among the environmental sustainability, of course, because both the projects are switching from fossil fuel based turning to bio-based one. So and there is also the innovation potential, so the technology that we saw. I don't know if from the speakers you want to add like something like related to some example, or where do you see most of the innovation potential in the solution that you propose today?
As a point of view of the material producers, it's clear that for Vito that we are an institution that its expertise is in sustainability. For us, the most important point is the environment and sustainability of the use of lignin or bio-based precursors. And this is because we have seen that fossil-based bisphenols, in our case, in Life Bible, have been very useful until now. It's been more than a decade that they are using these precursors. But now, in order to promote a circular economy, the reuse of the materials, the reshape, when it finishes the end of life of these composites, of these coatings, you want to recycle the substrate in case that you have fossil-based bisphenols or bisphenol A like a migration component or that is leaching from the material, this allows you to have a level of recyclability or reuse that is less, and this affects the sustainability. In case of lignin, since it's a bigger molecule, less reactive, it has this capacity of leaching much lesser, and also it affects less in order of ecotoxicity in the environment. For that reason, we think that this is the highest point environmental sustainability.
Yes, in the case of LIGNICOAT, we have not commented, but we are thinking, of course, in recyclability of the systems in the case of wood, for example, and the use of these type of coatings of lignin will help to this. So we are thinking in building developments and also in demolition and waste. So this is an important topic for us also, and we can contribute with this type of coatings.
Yeah, maybe I would also like to add a point as you of a chemical producer regarding the cost effectiveness. I agree at the moment, it's definitely not cheaper, but we are in a very early stage of the project and also of the material. And I would like to see in the future when lignin or wood is implemented and can be produced in big scale, the price will be reduced because it will be cheaper than fossil fuels. And I'm quite positive that, yeah, we are just starting right now using lignin, and in the future, there's definitely a way to implement it in the industry.
Yes, in the case of LIGNICOAT, we have involved in the stakeholders in the advisory board, the lignin providers. So we have continuous feedback with them, and they commented that in the manner that this market will grow, they will invest in the purification or even in modification of these raw materials. So in the future, for sure, we will have more. I agree with Claudia that we need a stable source of lignin and with the specific characteristics, because depends on the type of biomass, and also depends on the treatment to obtain that. So for sure, in the future, we will have more stable raw material and more cheaper.
To add a little bit what Aitor and Christine said, also when we are talking about cost effectiveness, as we have seen in the presentations of my colleagues and me, we are not using 100% of the materials is made of lignin. So only a part of the cost is regarding the lignin. We can use also other bio-based materials like glycerols or derivative of glycerol or other bio-based that are coming from fatty acids, for example. These could have different cost, but not the 100% of the material is made of lignin. Mostly we are talking about 50% maximum. So 50% maximum of the cost will come from lignin.
If I can add a word to the discussion, of course, I do agree that environmental sustainability is the main driving force in our case. But there are 2 points that have been voted less, and I would like to point out compliance with the regulations. And in my case, I particularly mean fire regulation in our specific market is the key of all. So to me, I need 100% compliance with the fire regulations, because there would be no product if it's not providing some compliance to the regulation. I understand this is very specific to the fire protection market. The other point is the performance characteristics. I've expected at the beginning that the performance would be poor, like always. We expect to happen when we change to a completely new material, especially if it is bio-based, because of the inconstancy of performance. I've seen at least 2 key characteristics that have impressed me positively. One is we obtained hardness, mechanical resistance, so probably durability, and this was a very good result. And the other thing was that the thermal stability of lignin can provide to some degree an intrinsic flame retardance into the material. So for the first time, probably I've seen a new green, still a completely undefined material that proves superior in some performance characteristics. I see this very positively.
Yeah, because it's usually the other way around, no? That we have the benchmark of what the fossil fuel industry is doing, and then with the bio-based, we are trying, to running after, to reaching their performance. And so in this case, yeah, we said that it's actually the green solution that may set some performance that are higher. So
only to some respects, unfortunately.
yeah, of course. At some point, the core was not the best, but okay, I think we have a pretty overview of what's the benefits in this bio-based material. We can go to the next one, which is on barriers. So what potential barrier do you see to adopting these bio-based materials? We indeed have lack of performance compared to the fossil fuel alternatives, cost concern, durability, availability of the feedstock. We saw, like, for example, some feedstock are less available, or there might not be yet a value chain, a supply chain developed for, let's say, addressing the need of this bio-based material. And yeah, we also put lack of consumer awareness or demand for this bio-based. I wouldn't expect that there is a lack of awareness. I think the market is pretty aware, and also consumers are pretty aware. So I don't think it's surprising if we don't see, well, some yes. So yeah, some results are coming in. Major one, the major choice of barriers seems to be the supply chain. And also, yeah, also lack of performance compared to the alternative already in the market. The speaker would like to, I don't know, mention something to this, to related also to your experience. Oh, I also open the floor to all participants. If they want to interact, they are free to raise their hands, and we can, if they want to share their experience of their perspective on this, I think it's also very much appreciated. So feel free to let us know or to write it in the chat.
I do agree that the supply chain is one of the key points that we should work on. Actually, I've been contacted by several companies in the last stage of LIGNICOAT. They read our things, and they called to say we do have lignin available for the market. We can talk about that, but I think there is still quite some way to go from these raw or lignin materials on the marketplace, if there are any for real, to those specific types and grades controlled in chemical, molecular weights, functionalities, and so on that we need in the coatings industry. So we need to cover the gap in between the pilot stage and the availability of a real material on the marketplace.
From the part of Vito that we are the connection now at this moment in technology-wise from the lignin providers to the resin producers or the formulators, the ones that we are able to depolymerize, extract and depolymerize the lignin to building blocks that are more defined and more reactive. This is developments that are currently going on I mean, 5 years ago, no one was doing the polymerization of lignin. Now we started with our 2 pilot plants. Hopefully, good results in the material size will give us and the industry reasons to invest in this kind of pilot plants. Also, we need to say one thing, that at Vito, we are not only expert in this kind of depolymerization or treatment of the lignin. Also, we work with different bio-based polymers, epoxy resins, polyacrylates, polyurethanes, polyesters, all that are coming from bio-based materials. And we observe what, as Saulo said, I think, Claudio said, that the raw lignin behave much worse than the depolymerized lignin, and it's a simple reason is problem of solubility and reactivity. If your lignin is not enough soluble in solvents or is not enough good dispersion in the other components that you are trying to do the polymerization, you will have aggregation in your final material or phase separation, and this will affect the performance of your final material. What we are achieving at Vito by extracting, getting the soluble part and depolymerizing this part until building blocks that are well defined, it's true in a range are not perfect structures all pure, but is a range of defined structures. We achieve to make more reactive points and make more soluble and well dispersed in the other components. So the materials, you can incorporate more quantity of lignin, and the final material don't present aggregation or phase separation, and the performance is better.
Yes.
Thanks, Claudio and Mark, for your perspective on this. I think it gives two different perspective, one more industrial, one more from the RTO. So it's also insightful for us, for participants, to see what two different parts think about this. What role do you think policymakers should play in promoting the adoption of bio-based material? So we have listed different options, so take your time to read them all, to see whatever apply. You can do multiple selection. Try to be comprehensive with the whole set of answer, but probably there are even more ways that policies can, let's say, push, accelerate the adoption of bio-based materials. So we have first, one of the role could be to establish more partnership. So to push for more partnership between industry, academia, and government to accelerate adoption. And then we have also something related to let's say to the financial incentives, both related to the product for company using such products, but also for coming up with this bio-based material, so increased funding. And then for adoption, okay, stricter regulation for limiting the other fossil-based, and also promoting the bio-based with the eco-labeling. So yeah, I can open the floor here for the speakers if they want to add some insight to this, if it respects what is your view on the role of policymaker in adopting, for pushing the transition?
Can I comment on those two that were voted less?
Sure,
and
that's
they are
also
connected with each other. Eco-labeling and public procurement, because there is a large number of eco-labeling schemes now on the market, and unfortunately, I fear also a large number of greenwashing. Eco-labeling is mostly voluntary, but it becomes kind of necessary in some types of works in the construction industry. And in many European states, some of them are enforced by law. in public procurement or in the general building. Like in Italy, we have the so-called CAM, the minimum environmental criteria. So these 2 points are interesting and linked to each other. And I think an eco-labeling would be useful, and it should be sound, objective, not keen to any kind of greenwashing, and particularly focusing on the bio content. All those that are on the market as bio content as a minor part of them. So probably a larger focus on green labeling for bio content of the material can be useful. And of course, one thing we need is clear standards to assess whether they are green or not. We do have analytical techniques for it, for example, and they should be specified. So these are 2 points that can be more useful, in my opinion, than just imposing rules or providing financial incentives to the market.
More on the end part of the product rather than the inception, so the promotion at the beginning. Yeah, but this also doesn't limit. I mean, we could also see some type of interconnection among these measures between establishing partners and at the same time even developing eco-labeling.
My point of view, for example, in construction, there are more and more initiatives, passive house, other type of initiatives that take into account the materials, and including, for example, LCA or the wall building. So I think it's positive, these aspects.
I think we can proceed to the final question. This is regarding future scenario. So after this, we will wrap up and close. So in your opinion, which of the following represents the most likely future scenario for bio-based material? Here we limited the choice to 1. We have 100% for bio-based material will coexist with traditional ones, each serving specific market segments, which I think it's not so unexpected from my point of view. I don't know what the other speakers think about this, or you would expected something else.
I would also agree to that point, because there will always be products that need to have very high regulations, for example, towards the strength, the chemical resistance, the UV resistance, or even for composites, if we are talking about flame resistancy for aerospace norms. There will always be a limitation, and it's not clear yet if bio-based material can overcome these hurdles now. So I would also totally agree that coexisting would be the best way to find the perfect market segments where bio-based material can fulfill the market then.
I will thank you. Thank you, the speakers. So I thank Christine, Mark, Elvira, Aitor, Saulo, Claudio. I think you were fantastic. You delivered a very great presentation, and I think you addressed very well the question that came in. And so thank you for your time, for your effort you put in this workshop. So thank you a lot. I also thank the participant. There were some interactions, so thank you very much for your thoughtful question. And I hope that the participant gave some insight on this project, and also some ideas. This workshop allow them to sparkle some ideas for bio-based materials. And I would like to conclude saying that we will share the slide and the recording with all of you, and there will be also a feedback form so you can let us know what you would have liked more to see, or what is your opinion from this workshop. So thank you again very much for joining us. It was a real pleasure to have you all here.
Thank you,
Thank you,
Michele,
Michele,
for being
for
a
the
perfect
organization.
Thank you,
chair.
Michele.
Thanks.
Thanks
Have a
everybody
good day.
for listening.
Have a nice
Bye.
day, guys.
Bye-bye.